We are on question 4. My blood pressure is rising cyclically, so I'm fatigued. I'm so fatigued. So before every lab assignment is due, my blood pressure tends to rise. Students ask last-minute questions. Increase in stress is cyclical and very fatiguing. You can look at my schematic of my arteries below. So arteries are typically in diameter, this in thickness. So right away, thin wall pressure vessel. What is my R over T? Is it greater than or equal to 10? And then I'm going to kind of orient my system as follows, right here. So one in one direction, two in the two direction. But let's check this out. So I'm going to go ahead and clear everything. So I'm going to click my kernel, clear. So I'm going to do that. My radius is going to be 150, actually 150 times 10 to the minus 6 divided by 2. So my thickness is going to be 6 times 10 to the minus 6. So my R over T is going to be this. Go, go, go. Here we go. Let's do that here. So let's look at this numerically. Let's look at this numerically. And what do you know? It is. So we are thin-walled. So once we're thin-walled, we know that sigma hoop is equal to delta P R over T. I know you're sick of this at this point. Sigma L is equal to sigma H over 2. And then my stress tensor in this particular problem is going to be sigma L, sigma H, 0, 0, 0, 0, 0, 0, 0. And then my strain in the hoop is going to be 1 over E times sigma H minus nu times sigma L. And my strain in the longitudinal E times sigma H minus, or sigma L, excuse me, minus nu sigma H. Doctor applies 2 strain gauges. There's a strain in the 1 gauge, so my strain in the 1, which is also my strain in the longitudinal, equals epsilon L is equal to 0.005. Yep. Doctor will diagnose me with blood pressure if it exceeds this. The strain energy release rate is this. The Young's modulus of my artery is this. So my E is equal to 10 megapascals. So let's go ahead and define some values. So Y is equal to 10 times 10 to the 6. I also know that my nu is going to be equal to 0.4 because it's a biomaterial, 0.4. So make sure to kind of write that down here. All right. And then I know that my E sub L is going to be equal to 0.005. So now I need to kind of, I need to figure out my delta P. So again, I'm going to define my sigma H is equal to del P times R times R over T. My sig L is equal to sig H divided by 2. And then now I can kind of go ahead and solve for the rest of these values for delta P. So I know that my E sub L, set that equal to 1 divided by Y times sig L minus nu times sig H. So let's solve for del P here. And so this is our del P. So 40,000. So this is my del P. And we said that we're high blood pressure if 180 times 133 if it's exceeded. So unfortunately, we have high blood pressure. So we need to watch what we eat and be careful. So we have high blood pressure. So don't do those late submissions. So write out the full stress strain tensor quantitatively. So again, once we have that, what's my sigma H, sigma L? What's my epsilon L? You know that. Epsilon H, that's going to be equal to 1 divided by Y times sig H minus nu times sig L. There you go. So that's my full stress tensor. What's the rotation to get to principal stress state? 0. Maximum shear, 45. If my blood pressure bursts, draw the fracture pattern. Ooh, I like this. So again, my hoop stress is always larger. Let's go up here. So I'm pulling more in this direction here, so it should fracture along this direction right there. Excellent. So what is my critical crack size required to fracture my blood vessel due to late submissions? Is it likely that my blood pressure will burst? So burst the material. So let's see what's going on here. So we have a stress. So our stress to burst is sigma H. So that's essentially, we're kind of testing, is this our, is sigma H, large enough? What's our critical crack size? So we have our sigma H. And we're also given this strain energy release rate. So when we look back through our fracture equations, we know we have several different parameters. So if we're given a fracture energy release rate, we can't use the Orawan equation. We need to use, or the Griffith equation, excuse me. We need to use the Orawan equation. So our critical crack size will be this equation right here. And our sigma H is equal to our sigma F in this problem. So we need to solve for, I need to solve that sig H set it equal to square root of y times g sub c divided by pi times a, and we're going to solve in terms of a. And I need to figure out what is my g sub c. So let's go back to our problem. So let's go here. And again, we could kind of double check, make sure that the units make sense, right? So my g sub c is 2,000. So g sub c is equal to 2,000 joules per meter squared. So let's look at that equation right there. So my stress, sigma F equals sigma H equals square root of, so I have pascals, which is a Newton per meter squared. A joule is a Newton per meter squared. So this gets canceled here. Actually, this gets canceled here. This goes away. And then divided by, actually, okay, so let's go ahead and look at this expression here. So my Young's modulus, so Newton per meter squared times a meter. So let's go ahead, we're left with, and then we're dividing by another meter. So it's going to be essentially a meter here. So it's going to be Newton squared per meter squared. We've got it. So that's going to be stress. So we're good to go in terms of our units. So once you define that, that's my critical crack length. So right here. So that's critical crack length for fracture. Is it likely? Well, we need to kind of figure out and see if it will burst. But that's a pretty large crack. I mean, looking at the size of your blood vessel, it's probably not likely that's going to occur. I'm worried about fatigue eventually leading to my blood vessels bursting. How many late assignments can I survive before my blood pressure bursts? I have initial crack length that is 10 nanometers. Also this, when I don't have to worry about late submissions, my blood pressure is a tenth of this, what it is during the late submission periods. So again, this is just kind of similar to what we've done previously in class and in kind of our solutions, but we will probably most likely, and actually definitely most likely, we are not going to be kind of going into a lot of these fatigue problems. So you won't have to worry about that. It would be mainly kind of this first part of this problem. So don't worry about D for this next coming exam. And then, yeah, that's pretty much it. So that's all we've got. So congrats. Get ready for exam 2. Come to the review session. I'll see you soon. Thanks.